No. Phase, no. Essentially, what I'm doing right now, I'm doing the last problem of the phase exam.
It's only for this part of the problem.
What do you mean you're gonna do the last problem of the phase exam in here? No, I mean like maybe they were similar like with Excel or something. But what do you mean, like today in class we're gonna do the last problem of the exam?
That's what they have started doing. So we're getting the partial molar quantities from changes in mixing, like that. If you look at the phase exam, that's basically, I'm doing the solution of the last phase problem, which is a major part of it.
Okay.
I just don't understand. You do your windows though.
I just couldn't separate them. This is very traumatic. Like, I wasn't planning. I wasn't planning to have to whole window.
It was very short.
It was horrible.
Oh, I should tell. Stick it up there.
Four.
Did you miss a 1 here? You put 4, but you wrote 14 here.
I put 4.
Yeah. That should be 14. Should it be negative 14? The picture's not live.
Welcome back, John. Students were asking about it. The students were asking about it. You were missed.
I gotta look at my notes on my 16th birthday.
All right, folks. I have a lot of things I need to cover. I don't want to be running. So, time to get started. So, we've been talking about frequency response. If we have a sinusoidal signal or sign, okay? If I have, for example, Z prime equals A sine omega t, and I go through a stable transfer function, with transfer function gz of s, ultimately, and ultimately is what we get as time goes to infinity, okay? If the input was reaching a constant value, we would be reaching new steady state. But will go to the ultimate solution, and the ultimate output is going to be also periodic with the same frequency as what is coming in, but different amplitude. So the amplitude is going to be the amplitude ratio times the amplitude of the input, and well, as I showed you last time, walking you through a rather hairy derivation, we found out, hopefully you can understand how you could show that the amplitude ratio which is the amplitude of the output, that's the amplitude of the output, divided by the amplitude of the input, can be obtained by taking the magnitude of the complex number that we get if we replace in the transfer function S by I omega, omega being the frequency of the input. And the phase lag is given by the argument of the complex number Gz of I omega. Clear, everyone? Any questions? Okay. One way to display frequency response is the body plot. Or Bode plot, I'm not sure the correct pronunciation. The body plot, okay, I should have got a color chalk. There's a little bit golden orange. I definitely color it. Text and MATLAB software normally produce a dual plot that has the same x-axis on both plots. The x-axis in both plots is the log of the frequency. The y-axis of the top plot is log of amplitude ratio. And the y-axis of the bottom plot, not log anymore, phase lag. And usually in degrees. Even though in equations you should be using radians here, in the plots it's normally done in degrees. So that's what you normally see in textbooks and in some software. We're going to be using for the rest of this class very extensively some software that goes with AAS 4323 underscore NP. I give you a little bit of the history of that software. Many, many years ago, 1982, I joined UF and retired the then analog computer. You just look at the on Wikipedia what an analog computer was. With what I could afford with very limited budget, which was a lab of 4 Commodore 64s. very proud in the name that it had 64K ROM. 64K, not megs, not gigs, K. And I wrote the software to create frequency response plots. Both the body plots we're going to talk about today and the Nyquist plots we'll talk a bit later about. Later, PCs became popular. I translated it into a PC program, which you have as EX5. The code of that, I'm a good practical programmer, but I'm certainly not a computer scientist. When I looked at that code a few years later, I wanted to hit myself. I've never seen such spaghetti code in my life. Go to commands, redirect you back down. The code was full of conditional go-tos. This condition, you go down the program. This condition, you go up the program. This condition, down again. This condition, up again. And when Windows XP came about, it stopped running DOS. I hadn't discovered, luckily for you, I hadn't discovered DOSBox, or DOSBox didn't exist then, I'm not sure. I couldn't run the program that was the mainstay of my class. And I didn't feel like asking students to spend $100 for MATLAB license, which is the student license. So luckily, my wife is a very accomplished programmer, and I gave her the Herculean task without knowing anything about control or anything like that, to take my horrible DOS spaghetti code and change it into a nice Windows program. And AAS are the initials of my wife, Asta is her first name, and that's the program we're going to be using the rest of the class, okay? And it runs on Windows. You may have to run it with a new Windows under, what's the right-click, administrator mode. Most computers will run directly, but in some computers you may have to run it the first time as administrator. Right-click on the file and select Run as Administrator. So that's the program we're going to be using today. And one change I've made in my programs, there is really no reason to have a dual plot with the same x-axis. And as a matter of fact, it makes things like the border stability criterion and things like gain and phase marking we're going to be talking about much easier to see if we combine them in one plot. So this is usual. This is class software. Both the original EX5 and the one you're going to be running, the AAS, will have the two in one plot. So left x-axis will be log amplification, and it's log base 10, by the way. The convention is to have log base 10 on the left. And I wouldn't have mind if it's the white chunk. But I'm so sort of orange. And that will be. So that's a body plot. And yes, ma'am.
Can you say what the orange one is different? Like, what's the orange one for?
The orange one is for the phase line. You have two plots. Here, top one is log amplitude ratio versus log frequency. Bottom one, phase lag versus log frequency.
Oh, I didn't know.
And here we combine the two in one plot, where the left y-axis is log AI, and the right y-axis is phase lag. Okay? So, the software will be drawing, given any transfer function, will draw for you the body plots. But let's see what the body plot would be for the most common transfer function we're meeting in this class, what's the most common transfer function we're going to be dealing with?
Open loop.
Say it, Alden? Exactly. First order plus time. So let's figure out what the body plot will be for first order plus time delay. So first order plus time delay, and I'm writing Z because that applies to U or a disturbance. Okay? So Z indicates either manipulated input or a disturbance as the transfer function K over tau S plus 1 e to the minus d. So what I want to do is figure out what the magnitude of that is as a function of omega for I omega. So this is GZ of S. I'm going to put here on S. So I need the magnitude of GZ of I omega and the argument of GZ of I. How am I going to get the magnitude? Well, if I can write the real part and the imaginary part, if I can rewrite GZ of I omega as real part of GZ of I omega plus I times imaginary part of GZ of I omega. Okay? This indicates real part. This indicates imaginary. Then, what would be the magnitude of GZ of I omega? You should be able to answer that. Someone other than Alden.
Oh, you have to like square up, like you did. It's like,
Square root of
Damn
the
it.
real part.
I was gonna say that.
Yeah, square root of the real part squared plus 6.
Okay, Kevin and 1. Square root of the real part squared plus imaginary part. And the argument of GZ omega would be tan inverse. We have several choices of inverses, but one we can use imaginary of GZ of I omega over a real part of GZ of I. So we could do this. However, we're going to do this only partially. I'm going to factor GZ of S as two parts. Let's rewrite GZ of S as GZ1 of S times GZ2 of S, where GZ of S is the part without delay, and GZ1 of S, and GZ2 of S is the e to the minus d. With me? Let's. Okay, this is my GZ of S. I can rewrite it as GZ1 times GZ. Okay? If I find the real and the imaginary part of each of these pieces,